Hello everyone and welcome to today's webinar, Simulation for Jamming and Spoofing, brought to you by GPS World Magazine and our sponsor, Jackson Labs. I'm Joelle Harms from North Coast Media, Senior Digital Editor for GPS World, and I'll be your event manager. Before we get started, I want to let you know today's webinar will be recorded. You're currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and also will be emailed to you tomorrow. So at this time, I'd like to acquaint you with the ways you can participate during the presentation. If you notice the Submit button in the lower left-hand corner of your console, if you have any questions during the presentation, just type it into the text box at the bottom left and click Submit to place your question in queue. We encourage you to ask questions throughout the presentation, and we'll address these questions at the end of the presentation during the Q&A portion. You can also use this space for if you have any technical difficulties or questions about how to use the console. I have an assistant producer, Allison Barwatz, is on the line, and she and I will personally assist you with those issues. You can also see GPS World's Twitter feed placed on the right side of your screen, so you can use the hashtag GPS World Webinar to also submit any questions during the webinar or to enter into discussions with other attendees. You can learn more about our speakers and moderator by viewing their photos, bios, and emails located in the upper left-hand corner of your console. And if you're logged in to any of your social media accounts, you can share the webinar's title, description, and URL with any friends or colleagues on some popular social media sites, and that's within the Share This widget. Also, keep in mind if you're viewing the presentation and see any URLs, all the links to those PDFs or resources will be on the left side of your screen under the Resources widget. So now I'd like to turn the event over to our moderator, GPS World Publisher and Editor-in-Chief, Alan Cameron. Hi, Alan. Are you able to?
Joelle, right, can you hear me?
Oh, perfect. Yes, we can hear you. All right. I think we lost you there, Alan. I guess we can just begin with the speaker lineup, and Alan can say a few remarks later on. So thank you, everyone, for bearing with us, and let's begin. So Paul, if you want to begin your presentation. Paul, are you there on the line?
Good morning, good afternoon.
Oh, great.
Spirent Federal Systems. We at Spirent have been very aware of the growing number of threats to GNSS systems over a number of years, and we have developed a mitigation strategy for that. If you're using GNSS systems for private use, if you're driving your car, if you're geocaching, for example, then jamming and spoofing could be bothersome to you. If you're using GNSS for critical infrastructure, then the problem is far more than bothersome. It could be life-threatening, in fact, and threatening to possibly even a nation's security. The U.S. Department of Homeland Security have identified that 15 out of the 19 critical infrastructure and key resource sectors have some degree of GPS timing usage. Both GPS time and GPS time and position are used in these critical infrastructure systems. The typical GNSS vulnerabilities that exist are, in addition to spoofing and interference, there are also errors in the GNSS segment, problems caused by the atmosphere. There are cyber attacks which are not over RF, and also multipath can cause great problems in GNSS systems. So some real cases of GPS jamming. The US Navy has actually accidentally jammed GPS for a period of time, and users onshore in the San Diego area were subjected to the problems of GPS signals being accidentally jammed. We've also seen that in non-US ports that non-US ports, many ships in the area were jammed as well. And at the DEF CON conference in August 2015, two Chinese gentlemen, Huang and Yang, actually demonstrated two different types of spoofing attacks on GNSS receivers. In the first case, they were able to fly a drone into a forbidden zone by spoofing coordinates to that drone. And in the second example, they misled a car which was parked in a parking structure to believe that it was actually in the middle of a lake. And with the advent of Pokemon Go, suddenly the number of experts in GPS spoofing dramatically increased in a very short period of time. Initially, spoofing was rather crude. People taped tablets to the blades of ceiling fans to make the tablet believe that it was traveling some distance, when in actual fact it was just going around and around. But then the type of spoofing attack became much more sophisticated, using some dedicated equipment, at least more dedicated than a ceiling fan. What motivated these guys to do this was financial. The value of high-value Pokemon Go accounts was in the several thousands of dollars, and so there was great motivation to start spoofing GPS. This all happened very, very quickly. That more sophisticated equipment that is now being used by spoofers of GPS, well, they're using low-cost software-defined radios, and here are a few examples. Open source code is available to allow the software-defined radios to be either GPS transmitters or GPS receivers. Of course, using them as GPS receivers is quite legitimate. Using them as transmitters is probably nefarious, probably illegal. So here we have some examples of GPS interference as has been captured by our detectors, sited in 4 different locations around the world. You see here that we have captured a number of different types of jamming interference, and these are actually real-world events. The great thing about the detector that we have is that we can capture, detect these events, and manipulate the data which is captured to create interference scenarios, which we can then play back into a unit under test in the laboratory, so we can replay them over and over again. In addition to being able to introduce interference, we can also use our SimSafe product to launch spoofing attacks. So we now have a very coherent, usable scheme for checking the vulnerability of a unit under test. And so we have this scheme for benchmarking receiver performance, which allows us to evaluate different receiver architectures. Even different firmware loads of the receiver could be benchmarked against a known repeatable test setup. In this particular benchmarking test, we have a fixed jammer and a moving receiver. The receiver will move from some distance from the interferer directly over the interferer and back out of the other side. The aim here is to evaluate at what range from the interference the receiver is impacted. And here we have a simulation of a spoofing attack on a timing receiver. Again, this is a benchmarking type system. The first of our simulators is simulating GPS live sky, a real GNSS signal. The second is actually being driven by SimSafe and is generating a spoof type signal. Both the live sky and the spoof signals are combined and fed into a timing receiver, which is the unit under test. We then test the performance of that receiver against a timing monitor to see how badly the timing solution is impacted by the spoofing attack. And here we have the results of that test, where we have the pink trace showing the output of the timing receiver, and there's a black line there showing a pseudo-range ramp, which we've introduced as a spoofing attack. And we see that the output of the timing receiver is very nicely drawn away from reality by this spoofing attack. And then as the attack finishes and we use a pseudo-range ramp to return to normal, non-spoof type signal level, the timing receiver actually recovers. You may also notice at the very bottom here that the timing receiver actually overshot the pseudo-range ramp, and also when it recovers, it actually also overshoots upon return. And so we have determined this action plan at Spirent, where we propose that you assess the risks using detection and characterization of the environment. You then develop tests against real threats. You then implement some mitigation strategy, improve the firmware in your receiver, and possibly reiterate going back to testing against those threats to see what improvement you've made to the performance of your receiver. And the insights that we bring here are, well, we realize that GPS, GNSS is always going to have a place in position, navigation, and timing for the foreseeable future. We know that threats exist. We also know that they're evolving as internet threats did, only in this case, the threats are growing much more quickly. So you need to perform data-driven risk assessments. You also need an operational strategy to deal with the presence of these threats. They're not going to go away. We strongly recommend a proactive strategy for robust position, navigation, and timing. A good system design actually makes things much harder for the hacker, and initial mitigation steps are achievable and straightforward, and full protection requires a system-level approach and thinking. Thank you, and I'll hand back to Alan now.
Thanks very much, Paul. And I apologize for my absence earlier. I had a phone glitch just at the time that I least needed it. But welcome to everyone around the world to this webinar on simulation of jamming and spoofing. I see we do have attendance from nearly around the world. And I'm just going to keep going, turn it right over to John Fischer, CTO of Spectracom, and I'll be back with you later to introduce our third speaker, Saeed Jackson from Jackson Labs, and handle the question and answer period that will follow. John, please go ahead.
Thank you, Alan. Before I start in, I'd just like to make mention of a major event that just happened a few hours ago, the launch of 4 new Galileo satellites. And so, as Alan said, a number of folks from all around the world are online. If any of you are from the Galileo program, I'd just like to offer my congratulations to you all that this is a major event in our community for these kinds of things to happen. And in fact, a little shout out to our sister company, Spectracom. They make the atomic clocks in Galileo and in a lot of these satellites, including the only space-based hydrogen masers. So quite an impressive event. And from what I just heard in the last hour, that all 4 even separated correctly. So our fingers are crossed that ends up being a successful launch to get 18 birds up there now. So so that is a good lead-in for this subject of the jamming and simulation. And so let me first just mention, if you don't know Spectracom, we simplify the integration of PNT things into our customers' systems. We don't make GPS receivers, but we make a lot of the things around them, including test equipment and stuff. So that's where I'll get into this then. So when it comes to testing GPS, and I'll say GPS, but I'm really meaning GNSS systems because there's so many constellations now. But when it comes to testing these things, there's jamming and spoofing. In my talk, I'm not going to make a differentiation between whether it's unintentional interference or whether it's intentional jamming. If it's hurting your receiver, it's hurting your receiver, and that's so. I'm going to call it all jamming for this thing. And then, of course, there's spoofing, which is where you're imitating the GPS signal. So, pointing out that jamming is very easy to do. But it's also very easy to detect. So, and we'll go into that of why it is. Spoofing is much harder to do, but it's also much harder to detect and then do something about it. So, so I'll go into all of those cases there. So, why is a signal so easy to jam? Well, as you probably all know, it's a very weak signal coming from space, and in fact, it's so weak it's below the thermal noise floor. And so I often get asked the fact that it's a spread spectrum signal, and spread spectrum signals, at least years ago, were a way of being an anti-jam device, an anti-jam method. But the problem is that the spread spectrum is very resistant to continuous wave or narrowband jamming. If you have any kind of broadband jamming and the fact that you have a very weak signal, it's not so effective. And so, and in fact, there are now all kinds of jammers. I think as Paul had mentioned in his presentation, there's a number of these, especially through software-defined radios. There's a number of more sophistication that you can do in jamming. And in fact, a few years ago, GPS World did a very nice article on what was called personal privacy jammers. And so I have a link there in the presentation if you want to look at that. But it's easy to jam. And in fact, the fact that the real signal is below the noise floor means that if there is any energy in the band, it's probably interference. And so just detecting whether either through your automatic gain control or some kind of signal detection, a pretty simple method is detecting if there's jamming is to see is there any energy in that band that's above the noise floor. And so I'll get into more things that receivers do, but more modern receivers now are detecting things like that. As I mentioned before about the fact that we now have multiple signals coming from multiple constellations. There are you have to start jamming. You got 400 megahertz of signal space now in this GNSS band. In fact, I'll show you a picture here. You have almost 400 megahertz of usable signal spectrum, so that if you have receivers that are using multiple constellations, multiple frequency bands, that'll be something that that might really help the anti-jam things. And so you want to look into what your receiver, again, it's going to be understanding what your receiver is doing to combat jamming, and you want to test for it. And you do want to test for it in whether it's different frequencies, in the different phases of whether it's acquiring the signal or is it being jammed after it's tracking, or what does it do? Does it reacquire? Does it coast? Does it lose the position? Does it change signal strength? Does it cause jumps? All those kinds of issues. So that's what you're going to be testing for. I'll go into a little bit more, but before, let me go back to spoofing. I mentioned that spoofing was difficult. Why is it so difficult? It really is a matter of, if you're going to spoof a receiver, you need to track it. You need to, the spoofer, the fake signal needs to be aligned in time, position, and power level. And so you really have to, whichever, if you're going to try to defeat a particular target receiver, you need to track it, and if it's a moving object, you're going to have to dynamically control all of these factors. So the perfect spoofer, and I always point out, those of us that make simulators, we are making spoofing equipment, because if we're doing it right, it is really a good spoofer. So it's something to be careful about, and in some ways it's almost like, I would call this like the equivalent of a Turing test of a spoofer, that a perfect spoofer really would be indistinguishable from the live signal. And so when you're testing, that's what you're going to want to be testing, is how perfect or imperfect can the spoofer be and still be a problem for your receiver. And so we make a system that can help you with that testing. We call it a vulnerability test system. And as I mentioned, to do both spoofing and jamming. To do spoofing, you have to make sure you're time synchronized, that your position synchronized, you're tracking. And so in a very similar way, we simulate the live sky, the true signal, and then we have a second simulator which we simulate the spoofer. And then in addition to that, we can add jamming. And so test your receiver under all of these conditions. So let me press on and say, okay, so what would happen if your system was jammed or spoofed? You do want to know, does it even notice it? Does it at least, at the very least, you'd expect your receiver to cause some kind of alert and not just fall silent. But does it give a malfunction? Does it give a position error or any kind of time shift at all? So those are the things you're going to want to test for. And as I mentioned before, depending on your receiver, what are the steps your receiver is taking? Is it using multiple constellations and multiple frequencies? Is it using other sensors? It's very common now for an inertial navigation system to be integrated in with your receiver. And so you can do, a receiver can do a lot of checking and agreement to make sure that if it's being spoofed or jammed, it can use the inertial indications there. So I've been asked by folks of, is there, receivers are getting smarter. Is there some kind of figure of merit or a measure of what makes one receiver better than the other? And the short answer is, I don't know. I haven't seen one yet. I do know that the U.S. Department of Transportation is attempting to, they are doing a adjacent channel compatibility assessment, and they've been doing a voluntary testing of lots of different manufacturers' receivers, trying to come up with at what point, mostly having to do with unintentional interference from other bands. So also, I do know that, in fact, recently the GPS Directorate has come out with proposed updates to their interface specifications. And in fact, they've added Appendix D, which will specify things that receivers should do in their processing to make them much more resilient to either unintentional or intentional jamming, to even some of the unintentional bugs, software bugs that have happened recently, things like that. So there are things going on, but so stand by, continue to look for things to go that we can make a measure of what really makes one receiver more resistant, more resilient than another. I have just one little example here of a test that we had run a while ago of testing jamming of a particular receiver, and this was kind of an eye-opener, a surprise to me. I would have expected that the receiver would have lost lock or things, but actually the jamming caused it to, this was a static receiver situation, and caused it to appear to be noisy and moving around noisily. Not something you'd always expect from just having some kind of a jamming signal. So I guess my advice here would be to expect the unexpected kind of thing, that there will be things, and so you're going to want to test all these different scenarios under dynamic conditions, or even under weird combinations. So I'll pass it back to other folks, but just to close off, to let you know that the threat is increasing. So if you didn't have to worry about jamming or interference before, you should start doing it now. You should start paying attention to it. Also, the receivers are getting better. They're doing more features to counter the threat. And again, thanks to these additional signals, additional constellations, like something like Galileo or GLONASS, or even the BeiDou system, which should be becoming global in the next few years. We'll have more signals. That'll be harder to jam, but you do want to start testing it. You should start worrying about it. You can find out more on our website. We've got some good information there, and so let me pass it back off to Alan, and you can hear more about from other folks. Thank you.
Thanks very much, John. Before I turn to Saeed Jackson from Jackson Labs, I want to tell our audience that in the question and answer period coming up after Saeed's talk, we are going to address multi-GNSS jamming and spoofing, and also adjacent band interference. Those will be a couple of your questions that I'll pose to the panel. Now, Saeed Jackson from Jackson Laboratories, please take it away.
Thanks, Alan. First of all, thank you very much to GBS World for allowing us the opportunity to present and host a seminar here. My name is Gregor Saeed Jackson. I'm the president of Jackson Labs Technologies. And for those of you that don't know us, we were founded in 2003. We have factories in 3 states in the U.S., and we manufacture all of our products locally. Everything is made in the USA. And our product focus is GNSS disciplined oscillators for timing and frequency markets. It used to be GPS disciplined oscillators, and now with the advent of GLONASS and Galileo, we're refocusing on multi-GNSS type of products. And we have more than 37 different product lines for commercial, industrial, and military markets. And for 2017, we're going down a brand new path. We're introducing a no-frills GPS simulator that we call the CLAW GPS simulator, and a derivative product which we call the RSR GNSS transcoder. RSR stands for Remote Secure Receiver. That's a product from Rockwell Collins, who we partner with, basically a SASM receiver, and our CLAW is basically form-fit function compatible to plug into that receiver and transcode GNSS signals, particularly to avoid jamming and spoofing type of attacks. The CLAW and the RSS transcoder that I was talking about were the products that we used for our presentation. We have a number of case studies where we went and actually simulated different scenarios on different target receivers that we have here and have supported and are very popular in the industry. And we wanted to see what the effects of these types of jamming attacks would be. So hopefully that'll be interesting later in my presentation. The claw itself is a very, very small. It's about the size of a deck of cards. Low cost, small size, weight, and power. Full constellation simulator. The target is we're going to simulate up to 16 channels, of which some can be reallocated to be, for example, multipath or other type of constellations will come later. And I mentioned earlier it's going to be a no-frills solution. It's going to be very low cost. That will hopefully allow these type of spoofing and jamming scenarios to be achievable by smaller companies that don't have large budgets. Target pricing right now, the introductory pricing will be under $3,000. The unit has a 63 dB attenuation range with half a dB resolution, which is well used in the type of case studies that I'll present later. And it's optimized for nanosecond timing and frequency applications. We primarily focus our products timing and frequency markets rather than the positioning markets. And so our main interest is to show what kind of effects these kind of attacks have on applications that require precise timing and frequency. One of the big targets that we had in the transcoder is to have a very low lag real-time simulation capability. Right now, in the pre-production alpha testing units, we're achieving less than 0.2 seconds, and the target is to have less than 0.1 seconds from when you send a NEMA position fix to the unit until the unit outputs that position on the RF channel. And one of the targets that we also do is we want to have the unit completely standalone, no PC required to operate it, and you can use any type of NEMA source to feed a position into it, such as another GNSS, an INS system, a SASM receiver. And as I mentioned, two different versions are available: a desktop unit and an embedded unit that is kind of targeted at GNSS transcoding applications. How does transcoding work, and how does it relate to spoofing and jamming? Transcoding for us is taking one type of GNSS signal, such as a SASM L2 signal with a PY code on it, and to transcode that into a clear L1CA code to avoid L1CA jammers, because most of the Chinese-made jammers, low-cost jammers that people can buy on eBay that are very popular with truckers, for example, they use the L1 band to jam and don't jam L2, which or even L5, which opens up an opportunity to use those signals to receive your position and timing, and using the transcoder, we can output an L1CA code to bypass those receivers. I'm sorry, those jammers, those spoofers. Some of the pitfalls in doing that is, do we use a live air almanac ephemeris, or do we synthesize the almanac and ephemeris? And obviously the advantages for synthesized almanac and ephemeris are that we can generate a perfect constellation that allow us to transfer the time and position and velocity information more accurately than if we had to recreate a live air almanac. And also we can use an IMU or INS and a cesium atomic clock where we encounter completely denied environments such as wideband spoofers. John mentioned a 400 megahertz bandwidth. Some of the higher end spoofers can do that. Below you'll see a block diagram of what that looks like. On the left side, you'd have a transcoder module with a NEMA input. On the right side, you'd have a target legacy receiver that you're trying to harden against spoofing and jamming attacks. GNSS transcoding is similar to simulating a GNSS signal. Basically, it's a benign spoofer where we're trying to recreate a GNSS signal that looks as real as possible. with the intent of transferring position, velocity, and time to a target receiver. We can use secure target PVT sources such as SASM receivers such as the GBgram or RSR or INS systems. And we can synthesize a constellation that basically uses a very optimal geometry such as perfect orbits with no clock error, no ionospheric delays. The tropospheric delays must be matched to the target receiver to achieve perfect transmission of time and position. So that's something that has to be kept in mind. It depends on the target receiver that you're trying to essentially benignly spoof what those models look like. And then some of the challenges there are that if you're receiving a position fix from your secure receiver at 1 hertz, you may want to interpolate that to a 10 hertz or 100 hertz output rate using accelerometers and integrated IMU, for example. Our first case study is something called a pseudolite. The U.S. military is very interested in avoiding or overpowering jamming scenarios by using their own, essentially, jammer spoofers that are distributed across the battlefield. They essentially output a signal that is very similar to a GPS signal. It uses M code or SASM-like signals with a time division multiplex. And it's transmitted locally at a power level that's about 10,000 times the power of a GPS satellite. So the received power will be about 90 dBm, minus 90 dBm at the receiver. And that'll allow scenarios where jammers are simply overpowered by local transmission of GNSS signals. So how do you simulate that? That's something that we're looking at right now to use our claw system to either simulate a pseudolite and at the same time to also simulate a jammer attack on that pseudolite. For those of you that are interested in further information, I put 2 links on the bottom of the slide there that have further information on the type of signal and effects of non-participating GPS receivers, because essentially to a non-participating GPS receiver, this looks like a jammer signal. It's only benign to authorized users that have the capability of receiving the signal. Our second case study is a jamming simulation where the goal is to check various different receivers that we have here for robustness against intentional and unintentional jammers. Using the claw today, we're able to do continuous wave and swept CW type of jamming, and in 2017 we'll introduce white noise jamming as well. And we're mainly focusing on GPS stimulation for the first versions of the claw. We're going to look at alternate GNSS systems as 2017 progresses, in particular GLONASS and Galileo. The setup we used for our testing is basically Jackson Labs M12M replacement GNSS receiver. That's a little receiver that is form-fit compatible to the very popular Motorola M12M timing receiver that's used in a lot of the timing stations around the world. Even today, that's a very popular receiver. And this basically is a form-fit function compatible replacement. We also have the original Motorola receiver to see how that reacts to our jamming scenarios here. It's based on a U-Blox MAT timing receiver, which is basically the latest generation concurrent GNSS receiver. It allows you to receive three different GNSS signals at the same time. We limit it here for these scenarios to GPS live over-the-air feed, which is about minus 115 dBm in our setup. Our setup is very similar to our colleague's setup that was shown in earlier presentations. We have basically two systems. And for this particular application, we're using an over-the-air live feed, antenna feed that we mix our synthesized signals into with a mini-circuits resistive combiner. And in this particular case study, we injected a jammer signal at minus 90 dBm, we're trying to overpower the over-the-air live signal. Now, in order to track the effects of this, we use a U-Blox application called U-Center, which is free for download from the U-Blox website via the USB port of our JLT M12M receiver. And that particular application has a spectrum analyzer, real-time spectrum analyzer feature that is not well documented, but if you contact uBlock support, they'll let you know how to enable that. That's really cool because you can see in real time the effects of in-band jamming on that receiver. So this slide right here is a clean live air signal. We disabled the jammers to give us a baseline, basically as to what the signals look like. You can see we have more than 40 dB CNO and a large number of satellites being received. On the bottom right, you see the spectrum analyzer. That's basically the 2 megahertz GNSS GPS band right there. Now we're enabling the jammer. The jammer is a continuous wave 1575 megahertz signal, so it's about 420 kilohertz off of the L1 center band, and you can see the CNOs have been affected slightly, but you can, most importantly, you can see the jammer showing up in the spectrum analyzer there at a rate of about 20, and those are not dBs, those are non-unit numbers that uBlocks provides. But most importantly here, with this very strong jammer enabled, you can see that we're still generating a fix, and we've only had an effect of a couple dB on the CNOs of this reception right here. And this is because the uBlocks receiver was able to detect the jammer and notch it out because it's a continuous wave, stable frequency jammer. Now we've enabled a swept jammer, and we're sweeping very, very slowly. So at this point, the sweep had reached about 30 kilohertz higher. And you can see that now the uBlocks receiver is absolutely not able to notch out the in-band jamming. You see the signal power went from 20 to about 250 on the spectrum analyzer, and you see that our CNOs completely broke down. You can also see the halos of the previous CNOs in the upper image there for the different satellites. That's the previously achieved CNO when we just had a stationary jammer. So you can see that even a slowly swept jammer is detrimental on GPS receiver performance. Moving on to the next case study, basically we're now moving into a spoofing simulation where we would like to test receiver vulnerability to position spoofing and timing spoofing. We can use either live air signals or simulated signals and mix these together. For our application, we actually used simulated signals and live air signal and simulated spoofer signals, so we have better control of the power levels. To spoof, we have to have a very precise time alignment to the spoofed signal to mask our attack. And that also requires, as mentioned by Paul, that you have to have by John, that you have to have a very good understanding of the position of the target receiver antenna, which is very difficult if it's moving, but it is possible to come up with that. And we also simulated what happens when you don't have a precise position knowledge of the antenna you're trying to spoof. Once we capture the target receiver, we can then introduce malicious effects such as position offsets, time offsets, frequency offsets, or corrupted nav data, which is very hard to detect. With two class simulators and a resistive power divider, we established time synchronization and use the internal automatic attenuator control of the claw to basically slowly ramp in the spoofer and to see the effects of that. And to be able to see the effect of the GNSS receiver moving over to the spoof position, we added a synthetic 50-meter position arrow so we can successfully identify what happens when the spoofer becomes active. In our first study, we used our M12M with the uBlocks M8T with a spoofed signal that ramps up from -40 to +23 dB relative to the live air signal over using a 12 dB ramp per minute. So the next video that you're going to see is time compressed from 5 minutes down to about a little less than 20 seconds. Hopefully this will come through in real time here. On the right side, you see the effects on the CNOs of the different satellites. On the left side, you can see the relative power of the spoofer. And the interesting thing here is that the U-Blocks receiver basically moves from one position to the spoof position. You can see over 5 minutes, we almost achieved a complete 50-meter movement of that spoof position. I'm going to repeat the simulation here so you can follow it once more. You see, as we slowly ramp the signal power, the U-Blocks receiver starts averaging the two positions it receives and slowly starts moving over to the spoofer as the power levels increase. And you see, once the power levels increase, it completely locks onto the spoofer. You see that in the CNO signals as well on the right side. The next simulation is the same U-Blocks M8T on our M12M receiver, but now we're ramping at much faster rate. We're ramping 60 dB per minute over 1 minute. So the entire simulation you're going to see now is happening over 1 minute rather than 5 minutes. And here you can see that the receiver is much better able to maintain position with the original live air position. And with a fast ramp up, we're only achieving about 10-meter position spoofing, even though we're spoofing the position by 50 meters. But with a fast ramp up, the U-Blocks is, I should say, smart enough to see that something is going on, and it's not immediately locking to the spoofer position. You can see that our CNOs are achieving 50 dB, but the position error is only showing up at about 10 meters. On the next presentation, on the next video, we did the same spoofer with a 5-minute ramp rate going from -40 to +23 dB, and with a 12 dB per minute ramp using the Motorola M12M receiver, which is an older generation, but still very well used receiver. On this simulation, the interesting fact is that the Motorola is able to hold on to its original position, and then at some point, as the power ramps up from the spoofer, it just jumps to the new position. And here we were able to jump to pull about 30 meters of position error out of the Motorola unit over a 5-minute period. I'm going to repeat this presentation one more time. It's pretty interesting to see the effects of the Motorola jumping position rather than slowly averaging between the two positions it's presented with. The next case study is basically spoofing for timing rather than position. Most critical applications such as cell tower communications, power generation, financial transaction timing are all localized with stationary position of the antenna, where the receivers are put into what's called a position hold mode that basically solves for timing rather than position. So it's on the one hand more difficult to spoof. On the other hand, it's much easier to determine the location of the antenna and to attack that particular system for timing. And the idea here is to pull the GPS discipline oscillator off frequency once we've captured the spoofed victim. We can do that by either changing the timing of the spoof constellation or by introducing errors such as UTC correction parameters and other nav data errors that allow us to pull the receivers off time. In order for us to gauge what the effects are, we added a 50-meter and 100-meter error later into the estimated position of the antenna. But the first simulation that we did was with a perfect antenna position. So we knew the antenna position of the spoof target and slowly ramped up power from -40 dB to +24 dB relative to the live air signals through a combiner. You see on the left side of the plot, the spoofer is disabled. Then we ramp up the power with no timing phase or positioning error. And then once we've completely captured the receiver, and this basically is a Motorola M12M receiver that's used at almost all of the NIST labs around the world to provide timing for NIST and for the National Standards Institutes and also power generation timing and other different applications. This is used, for example, in the very popular microsemi XLI system and so on. And you see what happens then is once we've captured the receiver, we can introduce a 10 part per billion frequency error into the constellation, and immediately you see that the receiver will take off and will follow the spoofed signal all the way up to 4.5 microseconds error over a couple hundred seconds. Now we understand that for power generation, for example, plus minus 1 microsecond window is critical to maintain. So you can see that here over a couple hundred seconds, we've already blown up the synchronization of the power generation plant that we are simulating an attack on right here. We also wanted to know what the effects were if your position, spoof position is incorrect. If you don't know the exact position of the GPS antenna and you're trying to attack the system and you happen to introduce a 50-meter offset. So what we did here is we spoofed the signal with 0 time error and 0 frequency error, but with an error of 50 meters relative to the spoofed victim. You can see once we turn on the spoofer and capture the receiver, that is causing a couple hundred nanosecond pull. I believe this is very similar to the slide that our colleague presented earlier. Now we've taken that a step further and we've introduced a 200-meter error relative to the victim, and we've let it run overnight, and this is basically the result. As the satellites of the constellation move in and out of view, you can see that basically the timing ramp is following the satellites and going up and down a couple microseconds here. Now this could be used to detect a spoofing attempt if you had a non-sophisticated spoofer that doesn't know the exact position of the antenna that it's trying to spoof. And lastly, what other attacks could we anticipate? Well, the spoofer, the attacker, could use the built-in receiver vulnerabilities. There's a lot of legacy receivers out in the field that have known firmware vulnerabilities, and without creating any type of position, velocity, or time error, we could attack just simply those vulnerabilities. One happened in 2016 in January, of course, sending out incorrect UTC correction parameters that caused a jump of over 13 microseconds in many timing receivers. Another known issue is the PRN32 issue. Early receivers assumed PRNs to go from 0 to 31 and would have a stack overflow if PRN32 became visible. That issue has mostly been mitigated by updating receivers. There's also a weak 1023 rollover, which is coming in April 2019, that could be exploited. Many receivers generate the wrong date. They go back to 1995, for example, causing all sorts of havoc. And we know that there are some receivers that have vulnerabilities to leap second events being flagged more than 30 days in advance of the actual leap second. This happened not long ago, last year. Some receivers incorrectly started applying the leap second right away, 5 months early. And then who knows what other possible firmware bugs could be maliciously exploited by spoofers that are not known right now. And that pretty much concludes my presentation, and I'll hand it back to you, Alan.
Thanks very much, Said. There's a lot of information in the slides from all of our presenters, and if you'd like to review that, go through it one more time. The link to the webinar presentation will be emailed to you within a day, and you'll be able to re-listen and re-look at the results and recommendations, and you'll be able to share that link with colleagues as well. We're going to turn now to questions from the audience, and we are going to run a little bit past the top of the hour, so stay tuned. First question is actually a double question, and I'll just open it up to everyone on the panel to address almost any aspect of multi-GNSS jamming and spoofing. The two questions that came in from two different people in our audience, one is how, John, you spoke about how difficult it is to spoof a signal, how difficult is it to spoof multiple GNSS systems at the same time? And secondly, considering that vulnerabilities of many of the signals are to some degree not shared, which GNSS is more susceptible to jamming, if there are any differences between the GNSS signals? Anyone from the panel take a shot at either of those questions?
Okay, I guess I could jump in on that first question of spoofing being hard. I'll speak for just really our simulator. Our spoofing testing is that once you're successful at spoofing one of the constellations, you can spoof them all equally then. The difficulty is tracking your target receiver, aligning your spoofer's position with what the target one is doing, aligning the power levels, aligning the time synchronization. But once you can do that for one constellation, at least within our simulator, then all of the constellations are aligned as well, and then you can now spoof all the constellations. So that would be the answer there. Now, that is a good lead into the second question of the idea that you can within a few dB, some signals are more stronger, harder to jam than others, but that's only within a few dB kind of thing there. That for the most part, if you have intentional jamming, the signals from all the constellations are so weak, it is just so easy to jam all of them that marginal one being a few dB stronger or a little better modulation technique and stuff, those are all just marginal things. In fact, I usually use the example of saying if you're trying to talk about those few dB and you're fighting interference, you're bringing a knife to a gunfight. You are the strength of even the simplest jammer is able to overwhelm any one of these signals. The real advantage of the multi-constellations is the multi-frequency nature. The fact that if you're just using L1 with a couple megahertz wide jammer, you can jam L1. Whereas if you're using all four of the frequency bands, you need to jam all four of them, and jamming 400 megahertz, that's it's doable, but it's a more complex and more difficult jammer. So I just say the multi-frequency nature is really what the strength of the multiple constellations.
Yeah, thanks, John. This is Cy Jackson. I just wanted to add that that's one of the reasons why SASM is becoming more and more ubiquitous and important. According to Rockwell, SASM receivers with their much higher chirp rate and wider bandwidth, resulting bandwidth, allow up to 30 dB or more robustness against jamming than simply listening to the CA code signal. So that helps, as well as there are companies that make available anti-jamming antennas that use null steering. And if you only have one jammer or spoofer and you know approximately what direction they're coming from, you can steer null into that direction and significantly reduce the impact of that jammer and spoofer. There are some lower cost solutions becoming available right now that anybody who's interested can contact us and we can get you in touch with those people. But those are kind of the approaches that people can do is multi-GNSS. The new receivers that are coming on the market allow 3 GNSS at the same time, so you can do GLONASS and the L1 Galileo and GPS. That'll give you 20 megahertz bandwidth right there for units that only spoof GPS, for example, may allow you to still receive GLONASS. And then, of course, the SASM receivers also use the L2 frequency as well as the PY code, which apparently gives a significant improvement in anti-jamming signal-to-noise ratio capability.
Thanks, Said. To all of our listeners, we're now at the full hour of the webinar, but I'm going to keep going for another few minutes just so we can address at least one more question from the audience, so stay with us. I want to ask our speakers to discuss almost any aspect of a very particular kind of adjacent band interference, simulating, that is, for something like the Ligado terrestrial wireless transmitters. The original question from the audience was how to best prevent jamming from Ligado mid-band spectrum, which may interfere with GPS L1. I don't expect in the context of this webinar we're going to address how to prevent that jamming. That's a very politically loaded question. But if you can just discuss simulation of events in that context.
Great.
Alan,
I guess I would
say,
go.
Oh, go ahead.
Go ahead, Said. Yeah, you go ahead. I'll jump in later.
All right, John. While we haven't simulated the Ligado spectrum, I think in our case studies we noticed that at least the very modern receivers are much more resilient to jamming and spoofing than the older legacy receivers, such as the M12, which like I said, is almost 15 years old, but still widely used in the industry. So I believe that moving forward, receivers will be more robust. I know that they have a 1 dB CNO reduction as a indicator of being jammed by Ligado. That's pretty easily achieved by any kind of signal. Like John mentioned, these signals are extremely low power. But I can say that probably moving forward, more modern receivers are much more robust than all of the billions of legacy receivers that are out there. In terms of simulating Ligado signals, I think that's something we could certainly look into, but it's tough because they're out of band, and so you could probably just take a signal analyzer and project a white noise into it, much like shown, I believe, by John's and Paul's slides previously. So I'll hand it to you, John.
John, are you there? Well,
Oops,
we may have.
Yes, I forgot to unmute. Sorry. Yeah, thank you, Said. I agree. The Ligado signals are fairly easy to simulate with just using like a standard signal generator. They're out of band and stuff, and so in all the things are pretty well. The characteristics are pretty well known, and as was said before, it's really it's an out-of-band interference issue with that. I guess the part that I would say is the best way to combat it is I think that's been answered by Javad of saying really you just do good filtering and stuff. So I guess the politically charged issue has to do with, well, what do you do with all these millions or even billions of receivers that are already out there that didn't have filtering. But I would say going forward with any new thing there, it's a relatively reasonable thing to be able to filter out-of-band interference from the L1 band, and just some good RF practices going forward should be able to do it. But to test for it, same thing. We do it with just a standard signal generator, mixing it in, and then we simulate the live signal. And as was said before, in fact, the Department of Transportation in there have recommended that a 1 dB degradation in carrier to noise as being the kind of test point for that.
Thanks, John. I want to thank everyone involved in the webinar. We're going to conclude now, a few final remarks. Thanks to our sponsor, Jackson Labs Technologies. This webinar would not be possible without them. Thanks to all three of our speakers, Paul Crampton from Spirent Federal, John Fischer from Spectracom, and Gregor Said Jackson from Jackson Labs. Thanks to you, the audience, for attending. You will, within 24 hours, receive a link to the webinar to review it and to share it. We hope you've enjoyed it. I'm sorry we could not get to our final question, which was regarding UAVs, simulation for UAVs, but I can hold out the hope of our next webinar, which will focus on UAVs, and it will be December 15th. Look for information on the website very shortly. Thank you again for joining us. Thanks to our speakers and to our sponsor, Jackson Labs, and have a great day, everyone.